All right, so where we last off, we were going to talk about these things having the same graph. Do they have the same graph? I think the answer is going to be no. H of x here. Log base 2 of 8. 2 to what power is 8? Wow, what in the world just happened to me? Well, if they have the same graph, they should be equal, right? Is 3 plus log base 2 of x equal to log base 2 of x plus 8? No way, right? So, they don't have the same graphs. We could say because h of x does not equal k of x, right? The only way they can have the same graph is if they're the same function, yeah? That makes sense.
Why does that suddenly change those three names?
Okay, good question. Log base 2 of 8. 2 to what power is 8? That's why. All right. Why are the graphs of 4 to the x power and 2 to the 2x power identical? Well, f of x. Can I write that as 2 squared to the x power? Which is the same thing as 2 to the 2x? So why are they identical? Because f of x is equal to g of x. If they're the same function, they're definitely having the same graph. All right. Okay, so let's go ahead and graph these. And let's keep in mind, okay? Let's look at g of x a little closer, a little more closely. G of x, can I write that as 2 squared times 2 to the x power? Right, 4 is 2 squared. Don't we have a property of exponents that says that we can add those exponents and keep the base the same? So this becomes 2 to the 2x. So isn't that the same thing as h of x? So clearly those graphs are going to be the same. Those graphs will be the same.
When does it turn out?
Huh?
If you multiply the 2, what's the turn? 4, 2%.
No, because the bases are the same. The exponent there has that all locked together. So you can't multiply the 2.
Oh, that was exponents.
Remember, the rule of exponents.
Yeah.
Cool. Hey, let's go ahead and graph these. So I'm going to make a table with x, f of x, and g of x, because right, f of x is 2 to the x power. I'm going to just write that down here. So what happens when I plug in -2, 0, 1, 2, and 3?
you just pick those numbers at random?
Yeah, kind of random. They're smaller, so they'll be easier to calculate. And then I chose some numbers that are on the negative side of the y-axis, and then I chose some that are on the positive side. So that I know kind of what's going on both sides of our y-axis. So if I plug -2 into f of x, okay, that's f of -2, so that's 2 to the -2 power, which is what? It's 1/4. If I plug 0 in there, I get 1, right? 2 to the first power is 2. 2 to the second power is 4, and this is 8. Okay, so now we can graph f of x. Let's do it. So at -2, I'm at 1/4, so this is like way down here, right? And then at 0, I'm at 1. And then at 1, I'm at 2. At 2, I'm at 4. And at 3, I'm all the way up at 8. And it's going to keep going up like that. Right? There's my points. Hey! What values can x never take on? Yeah. Well, I mean, sorry. Yeah, can f of x never take on, right? X can be negative, but I know what you're thinking. You're thinking of the fact that you can't plug in any number for x, right, and get a negative number, right? It'll never happen. So that's why this is happening. Why can't it be negative? Because the idea is okay, is there a number that you can plug in there and for x that outputs a negative number? There's no such thing, right? And that's why for very large negative values of x, we get values of y that get closer and closer and closer to 0, but never touch, right? It turns out that there's what's called an asymptote right here, which is just a line that your graph approaches but never touches, right? Remember, it was the friend zone. Yeah, you'll get as close. You can get very close, but you're never gonna touch. That's an asymptote. All right. All right, let's come up with a table of values for g of x, which is going to be 2 plus x. So, when x is -2, g of x is 1, right? Because that becomes 2 to the... So let's go, we'll bring this down here, and this is just g of -2 is equal to 2 to the 2 minus 2, which is 2 to the 0 or 1, right? That's what I'm doing when I'm filling out that table. So how about 1? When x is 0, we get 4 here. When x is 1, we get 8. When x is 2, we get 2 to the 4th power, or 16. And when x is 3, we get 32. That's going to be off our graph. But let's go ahead and graph it. And so we have -2, 1. And we have 0, 4, 2, 8. Sorry, 1, 8. I'm sorry, that is incorrect. The point is 1, 8, 2, 16, and then we go off the chart. So this is going to look like this. There we go. coming up with lots of random kinds.
I'm still going to.
Huh? Yeah, in my brain. Okay, there we go. We graphed them as we were instructed to do. And that's all we have. First of all, when we're graphing this, they're trying to trick me with this h of x, right? Because 1/2 to the x power, isn't that the same thing as 2 to the negative 1 to the x power? 1/2 is the same as 2 to the negative 1. So that's just 2 to the negative x, which is the same thing as g of x. Do we know that h of x and g of x are the same? I'm going to make a quick table of values for this. And we can choose the same values, negative 2, 0, 1, 2, and 3. And we already determined that this is 1/4. 1, 2, 4, 8, right? We've already done a table of values for f of x on the previous page. So let's see about g of x. What happens when I plug in negative 2? Well, I wind up with negative 2, which is, yeah, it's going to be positive 4. So, whoa, okay. When I plug in 0, negative 0 is 0, so I get 1. Yeah? What happens when I plug in negative 1? I wind up with 1/2 there, right? 2 to the negative 1 power is 1/2. When I plug in a 4, I wind up with 2 to the negative 2 power, which is, we determined was 1/4, and then this becomes 1/8. So I keep getting closer and closer and closer to 0, yeah? Well, let's go ahead and graph each of those. We know f of x looks like this. It's got, at negative 2, it's at 1/4. At 0, it's at about 1. At 2, we're at, or at 1, sorry. At 1, we are at 2. At 2, we are at 4. At 3, we're at 8, and it keeps going. And so here we go. We graphed this one last time, but let's go ahead and graph it again. All right. All right. Let's graph the other one. At negative 2, I'm at 4. Weird, right? At 0, I'm at 1, so they share that point. At 1, I'm at 1/2, so like there. At 4, I'm at, sorry, at 2, I'm at 1/4. So this thing obviously is going to go like that. And don't you think it's probably just going to continue up? So what happened? What did I find out? I found out that when I make that x negative in my exponent, I'm reflecting it about the y-axis, which is the same thing as the line x equals 0.
Pictures you showed me. Just the way you moved the camera.
Okay. So, now let's get down to the nitty-gritty. Down to the nitty-gritty. So what happens when we transform stuff? So, we're going to get out our calculators and we're going to look at what happens with each of these. I'm going to argue, and I'm going to use my calculator to show you that this is true. That when I have a 3 out here, right, and I'm comparing it, what we're doing is comparing to, let's compare, they've used f of x, so let's compare to h of x equals log base 10 of x, okay? We're going to compare g of x to this h of x. I'm going to argue that if you're compare h of x to g of x, this 3 is going to be a vertical translation of plus 3. It's going to go up 3. This 2 is going to be a vertical scaling it's going to look like a stretch. It's going to look like you stretched it vertically. And this 2 over here is going to be a horizontal translation. Got a horizontal translation? It's going to be plus 2. It's going to be weird. Let's look at it. I want to look at each of those separately using our calculators to show what's going on there. Okay, so let's look at what's going on with these transformations. Let me clear this out. All right, so this is the graph of log base 10 of x. Yeah? All right. So let's look at each individual piece separately using our calculators, right? Because we have our calculators out right now, and we're graphing them and looking at it. All right. So we've graphed that. I'm going to do the 3. Okay, see this 3 right here? That one right there? Yeah. Hi, pretty. Just kidding, sorry. So what happens when I add the 3 to this? What do you think happens? Heck yeah, it does. It goes up 3. Let's prove it. Boom! All right. Let's look at what happens now if we multiply it by 2, because we've got that multiplication by 2 in there. Let's look at that separately. I really like doing this stuff. I think it's a good way to see what happens when you add, subtract, multiply functions. What happens to their graph? How does it transform the graph? So this one's harder to see, but what happened is, it's like you grabbed it and you stretched it, right? In this direction, in the vertical direction. Looks like you took it and you stretched it in the vertical direction. Not super obvious with log base 10, but if you were to do this with like log base 2, that's a little more compact, you would be able to see a big difference, a lot bigger difference. All right. So that was a stretch, as I told you, just proving it to you. What happens when we go, and this isn't on there. This is not on there. What happens when we go negative log of x? We reflected it about the x-axis, right? So we made a reflection. With negative log of x. Cool. It's not on there, but I thought it was cool to look at. The last one we need to check out is what happens when we take log of x. Was it plus 2? Minus.
Stop.
I won't, thank you. It shifted it in the positive direction 2 units. All right, cool. So just wanted to give you guys a graphic look at what those transformations are. And if you're being asked what transformations are on a test, just do them separately in your calculator, each one separately, and you'll be able to describe what each number is doing to the graph of the function. Cool? It's a really easy way to approach it. Not a lot of math or memorization involved. Just have to know how to use your calculator. Right? Moving right along. let's actually graph them by hand now, all right? So, okay. So if f of x is, so we're saying f of x is log base 10 of x. Sorry, I said that was h of x, didn't I? Or was it k of x? It's now that's what it is. So, hey, I only want to graph like whole number values, right? For log base 10 of x, there aren't going to be very many things that I could plug into x that will output a whole number value, right? Not a fraction or a decimal. Those numbers are, well, obviously you can't plug 0 in there, right? There's no such thing as log of 0. What if I plug 1 in? 10 to what power is 1? No. So 1, 0. So, okay, I have a point 1, 0. 1, 0. Okay. And then what's my next value that I can plug in and get a whole number? 100 is 2, right? If I plug x for x is 100, I get 2. But that's not on my graph, right? What about for the next one would be 10, right? If I plug 10 in here, what is log base 10 of 10? 10 to what power is 10? 1. But it's okay, that's good enough for me to graph it because I know what log of x looks like, right? So I can go to 10, 1, and now I know that this thing's got to go real close to 0 over here, and then make a turn, and then my next time that I have, like, it's going to hit 2 way, way, way over there at 100, right? It's not going to get to 2 till it gets all the way over to 100. So that's cool. I can make a sketch of the graph with just those 2 points, because I know what the graph looks like. Let's go ahead, and if g of x is 3 plus log, well, sorry, 2. 3 plus log, dang it. 3 plus 2 log of x minus 2. Let's graph this by hand, okay? So we got x, and we got g of x. So I want to think of clever numbers that I can plug in there so that I get whole number answers, right? If I got to graph this by hand, I don't want to have to graph 1, 2, 3, 4, 5, 6, 7, 8, 12. 12 is 1. 12 works. If I plug 12 in there, I wind up with a 10, right? And then 2 is the other one. Those are the only 2 that are in my range of my graph that will work. So why did those work out? And I'm going to just kind of move this over here. Ooh. Whoops. Let's look at g of 2. G of 2 is 3 plus log base 10 of 2 minus 2, okay? Just plugging in 2 for x. So that's 3 plus log. Uh-oh. I want to have a log of 0, right? I don't think 2 works. Because I can't have log of 0, right? So we should try a different one. Maybe we go one more. How about we go 3 instead? That's interesting. So 2 is not on my graph, right? If 2 is not on my graph, then it's like there's a line here, right? That my graph is going to approach but never touch. A friend zone line. The friend zone line. You guys making stickers of me again? I'm not eating a banana today. Hey. Okay. So we realized just now that x can't be 2, right? So I'm pretty sure that x can't be 2, so I'm pretty sure that that's the line that our graph is going to approach but never touch. So let's plug in this one. 3 minus 2 is 1. What log 10 to what power is 1? 0. So I get 3, so I have the point 3, 3. What happens when I plug 12 in there? If I plug 12 in here, I get 2. Oh, I'm sorry, and that's supposed to be a 2, and that's supposed to be a 2. 2 times 0 is 0, though, right? Let's go ahead and plug it in. Let's go g of 12 in here. So that's going to be 3 plus 2 times log of 12, 2 times log of 12 minus 2, which is going to be 3 plus 2 times log of 10. What is log of 10? Log base 10 of 10 is 1, right? So we get 5. So if I plug 12 in, it outputs a 5. That's enough that is enough points for me to graph this thing by hand. So let's plot the point 3, 3. And then we'll plot the point 12, 5. We know that x can never be 2 or less than 2. So the graph looks like that. There we did. We graphed it by hand. Which 2 points?
The line.
So I'm graphing 2 different functions. I'm graphing log of x, and I'm graphing. Never mind. Yeah. No, it's okay. All right, let's look at this one. So again, we're going to look at these transformations. I'm going to argue that this is going to be a horizontal scaling, the 2. That 2 is going to be horizontal scaling. And this 1 is going to be a horizontal translation. Let's go ahead and check this. What happens to these things in the calculator, all right? So back to our calculator. We're going to compare graphs to the graph of 3 to the x power. That's what 3 to the x power looks like, okay? So let's see what happens when we multiply the x by a 2. As I said, it was a horizontal scaling. It's like a squeeze. It's like you took it and you squeezed it. And it kind of squeezed. Right? As we saw. 4 minutes. Yeah. The clock's wrong. Okay. Now that we looked at that, let's see what happens when we go x. It says plus 2, right?
No,
Plus 1, thank you. comparing that to the graph of, it looks like, to the graph of 3 to the x, it looks like what we did was a horizontal translation to, in the negative direction 1. Okay? Because we added 1 to our power. Alright? Real quick, it's not on there, but I want to look at this as well. What happens if we go 3 to the negative, 3 to the negative x power? What happens there? Ooh, it's a reflection about the y-axis. Alright, so now with that stuff in mind, let's go ahead and answer some questions here. What is this going to be? Well, first of all, they're trying to trick us. Because isn't that the same thing? Isn't 9 to the x power the same as 3 squared to the x power? Which turns out to be 3 to the 2x. And we said that if we multiply the x, it's going to be a horizontal scaling. It's going to be it's the dilation. It is a dilation. So this is horizontal scaling. In the form of a describe graph of G as a transform. All right. And we already described C, right? All right. What? Woo! It says to graph the graph of G using transformations, but I'm not gonna have time. So we'll finish this one. We'll graph these tomorrow, and we'll finally finish this lesson, and then we'll get into lesson 20 as well.